So this is conceptually pretty steep here. So what we want to do here is that we want to now go in and we want to look at two-body collisions in one dimension. Okay. So here's what we find. There are two categories of collisions. One is called elastic, and the other one is called inelastic. So what does elastic mean? Elastic means that there is no loss in this term called energy. There's no loss in energy in the system. Inelastic means that there is energy loss from the system. The problem is we haven't talked about energy. Okay, we haven't talked about energy. So what I need to do here is that I somehow have to get in and explain to you, what do I mean by energy? A little bit, not too much, but what do I mean by all these terms here? So what I want to do here is that I want to talk about what do I mean by an elastic collision versus an inelastic collision. And it's essentially what it's telling us is, where does the momentum go? It's two different things, unfortunately. So let's start off by what is a perfect elastic collision. Okay. So a perfect elastic collision, it has no sound or generates or does not generate any heat. So it has no sound or it does not generate any heat. So what does that mean here? So the first thing that we want to do here is that what happens when we drop a ball? So our focus is dropping a ball onto the floor. So what do we mean when we say we drop a ball onto a floor? So I imagine that I have a ball and I'm going to drop it from some height, and this ball is going to head down and it's going to collide. So a lot of times people will say, oh, that's part of the collision. So that is not the collision, but the collision occurs right before / after. So what I'm looking at is that I'm looking at something like this here. So I imagine that I have a floor right here. And what I see here is that I see the ball. So here's the ball. And when I see the ball, this is right before it hits the floor. So I see that speed of the ball, and this is what I call V1. This is my before. And then afterwards, the ball is coming back up. And this guy is now headed in that direction, V2. And then this is afterwards. So when we talk about a collision, it's a collision at the ground. It has nothing to do with the height. It's right before. So now, what's a perfect collision here? So a perfect elastic collision bounces back up to its original drop height. So if I have an elastic collision and I'm seeing my floor right here, right? And I'm seeing the process that's going on, I then see, here's my ball. And then right before it hits the ground, it's right here. So I drop it. So now it comes in and it has some speed or some momentum that looks like this. Right after, I now have a collision, and then it reaches up to the exact same height that it actually was dropped from. And so when I look at the situation, these two situations here, you could see that they have the same height. If they have the same height, that means no energy was transferred to sound / heat. They always go back to the same height. By the way, this is impossible. It does not occur. In the case of an elastic collision, so then if I ask the question, what is an inelastic collision? We say some energy is transferred to sound / heat and not into motion. So if I'm looking at this, then I could look at this same situation as right here. I could come up here.
So in reality, basically all collisions are inelastic then, because
Elastic.
a normal elastic one's not possible, right?
I would agree with you.
Okay.
There are situations where they make them closer and closer.
So basically just getting closer to getting an elastic.
Yeah.
But not really.
And so what happens in this situation, so then if I have a ball that's coming up like this, what you'll see here is that as the ball rises up, it's not at the same height. But during this process, what you're going to find here is that the ball actually heats up and the ground heats up. And what you're also seeing here in this situation here is that you're also hearing the collision. But the key thing here is that it's not at the same height. So in a lot of ways, elastic is sort of like this massless particle, massless string. You have to look at it relative to the number of sig figs that you want. If the number of sig figs that you want is really low, then you might be able to get away with an elastic collision. But the vast majority of the time, that's not the case. So what I want to do here is that now I want to apply these elastic collisions, which are more challenging. Actually, inelastic is more challenging, as you'll find out. But it depends on how it's set up. So what I want to do here is that I want to now organize different possibilities of elastic collisions. With momentum bar diagrams. Man, the physics behind collisions is so phenomenal. There's some really crazy things that you can do with collisions. I don't know if I want to get into it. Maybe in 4A, I'll definitely get into it, but not here. But there's some really, really fun ass stuff that you can do. There's no doubt about it. So let's deal with the simplest one. So I'm going to break this up into cases. So this is going to be case one. And case one, we're going to focus on elastic collisions. I know that we are, you know what? Case one is not going to do that. We already said elastic collisions. I'm going to say that this is equal masses. So when I say equal masses, of course, that means M1 and M2 are the same. And one visualization is that you can think, I believe all billiard balls are the same mass. I don't know the answer to that, by the way. So I imagine that I have a pair of billiard balls that we're going to shoot at each other and they're going to collide. So I need a before and I need an after. That becomes super, super important as we go through this in this course here. So now, what do I see here? I have two billiard balls. So for the sake of simplicity here, I imagine that I have a ball coming in here. And every single time, what I'm going to do here is that I'm going to imagine that this green ball right here, which I'm going to call ball 2, is always going to be at rest. That means its momentum, P2 initial, is going to be 0. It's just going to make life easier for us here. Okay? So now, I got to pick a different color. So how about if I choose blue for the projectile? And this guy is always going to have some momentum coming in like this that's not 0. So this is going to be the setup. So in this case, P1 is called the projectile. P2 is called the target. Or maybe I should just say 1 is the projectile and 2 is the target. So now I start to analyze my system here. I'm going to say, here's my system. So if this is my system, and then I ask, are there any forces? Do you see, I don't know, gravity would be perpendicular to this, so it's not going to apply anything. Are we talking about friction here? Nope. So what I'm seeing here is that the external forces here are zero. Therefore, the total momentum of this system is a constant. So what does that mean? So let's start drawing a bar diagram of the system. So if I look at this system, it says this. If I have this amount of momentum initially, then you could see that the only momentum that I have here is of P1 going in this direction like that. And the reason why that's the case, because we can see here that P2 has zero. So what I'm seeing here, according to conservation of momentum or dynamic equilibrium of systems here, that momentum, that blue momentum bar has to be before and after the collision here. So what this is really telling us here, so when I look at this guy right here, this bar is telling us is that the total momentum must continue to move to the right, no matter what. But at the same time, one of the things that we said here is that momentums must exchange / readjust their momentums to conserve P total equal to a constant. So if there's an exchange here, then it means that P1 goes to P2 final and and P2 initial. How do I gotta draw this. That means here that then P1 final is exchanging its momentum to P2 final. So P2 final would then go like this here. That's the only way you can conserve momentum here. This is a pretty hard one to really comprehend. So that means picture-wise, it would go like this. I would have P1, and what P1 is going to do now is that its momentum here afterwards is zero, and then P2 is then going to have P2 final, which is equal to P1 initial. Oops, not that one. And this is what 2 is going to look like. That's what I mean about the exchange of momentums. So now let's go to a second situation. Let's go to case 3. Or case 2, excuse me. So here, we're going to have a massive target that's going to be shot. In other words, M1 is going to be much more massive than N2. So I could imagine that we shoot. Wait. Massive target. I got it wrong. Not a massive projectile. It's got to be the opposite way. So we shoot a golf ball at a bowling ball. I don't know if you've ever thrown a golf ball at a bowling ball. Yeah. You want to be careful. All right. Maybe a helmet, safety goggles, face mask. Yeah, you want to be careful. Turns out to be pretty dangerous. And nobody is safe. I'll tell you that right now. When I was in college many years ago, we did something very, very similar to this, where I was in the dorms. My right behind my dorms was the football stadium as well as the baseball stadium. And during football season, the baseball stadium is empty. We used to drop baseballs with basketballs off the top of the baseball stadium. That's like throwing a golf ball. Actually, it's worse. It comes off much faster. And the first time I saw one of those baseballs hit somebody, you went like, oh shit, you better be careful. So collisions can be fun. I'll tell you that right now. So what do we want to do here? Let's physically interpret what do we expect here. So what's going to happen here? What do you expect here? What do you expect? If you throw a golf ball at a bowling ball, do you expect the speed of the golf ball to change much? No. So we expect that the golf ball's speed does not change much after the collision. Like if you have a really, really solid ball and a solid wall, like a super ball. So if you throw it at a hard wall, watch that super ball come back at you. Oh, it's coming back at a high speed. So we don't expect the golf ball to lose that much speed. In other words, we're saying that the initial speed should be approximately equal to its final speed coming back. Okay? So if we're looking at this thing, what are we actually seeing picture-wise? So here I go. So I have my golf ball. Right? Here's my golf ball that I'm throwing at, and it's one, and it has this much momentum coming in. So if I have a bowling ball, you could imagine that this bowling ball is going to be quite massive. And this is what I'm going to call 2. So if I look at this thing from our previous arguments, this is our system. This is what happens before. So if I go and I look at this thing afterwards, what do we interpret here? Well, we interpret here that after the collision, we're going to see that golf ball moving pretty fast, coming right back at you in the opposite direction. And then we would expect here that the bowling ball to be moving slowly to the right here. So we expect that this guy is then going to be going like that. So now, what about the momentums? Does the bowling ball have a small momentum? Does the golf ball have a high momentum? Which one has the bigger momentum? The bowling ball or the golf ball? Right? That's really the question that we're asking right here. Which one has a high momentum? And it's the bar diagram that has to answer that question. Let's look at the bar diagram. So here is the momentum of the golf ball. And we know that the momentum of the golf ball is coming in this direction. We know for a fact here that the momentum of the bowling ball initially again is 0. So this tells me that the total momentum of the system has to be fixed. So P total must be fixed. And we already talked about this situation. So I know here is that if this guy comes back with almost the same momentum, going back in the opposite direction, and you could see here, again, this is the negative direction, then what happens here is that look what the bowling ball has to do. What does it has to do? It has to stop the ball. And then to conserve momentum, it has to be going above it. So you're seeing that the vast majority of the momentum is with the bowling ball. And what you're seeing here is that in this case, the reason why P1 has such a big momentum is because it has a high speed. The reason why this guy has such a huge momentum, even though it's moving slow, it has a large mass and a slow speed. So this is the bowling ball after the collision.